Now we will start the chapter Gas Laws and Kinetic Theory of Gases. So first we'll see the properties of an ideal gas. In an ideal gas, all molecules are identical and spherical. These molecules have exactly equal coefficient of pressure and volume. The size of these molecules are very small. There is no force of interaction between these molecules. All the collision between different gas molecules are perfectly elastic in nature. When you talk about an ideal gas, there is no effect of gravity, and all the ideal gas, they strictly obey the Boyle's law, the Charles law, and the law of pressure in all conditions of pressure and temperature. Now we will go through different gas laws. So first let's see Boyle's law. Boyle's law is also called isothermal law. This law states that volume of a given mass of an ideal gas is inversely proportional to its pressure at constant absolute temperature. So according to Boyle's law, the volume of a given mass of gas is inversely proportional to the pressure at constant temperature. Here V is the volume, P is the pressure, and T is the temperature. So according to Boyle's law, PV is constant. So for a given gas, we can say that P1 V1 is equal to P2 V2, which means that suppose at any given volume V1 the pressure is P1, then this product will be equal to P2 V2, where V2 is some other volume and P2 is the pressure of gas at that volume. So this is our Boyle's law. PV is equal to constant. Now we will discuss Charles' law. Charles' law is also called isobaric law. This law states that volume of a given mass of an ideal gas is directly proportional to its absolute temperature at constant pressure. So according to Charles' law, the volume of a given mass of gas is directly proportional to its absolute temperature at constant pressure. So from here we have V by T is equal to constant. So suppose at some pressure P, if we take a volume V1 of a gas, and if the temperature is T1, then at the same pressure, if we increase the temperature, say increase it to T2, then the volume will also change. Say the volume will change to V2, then this ratio, that is V1 by T1, will be equal to V2 by T2 at constant pressure. So this is our Charles' law. Now we'll see pressure law, which is also called isochoric law. This law states that the pressure of a given mass of an ideal gas is directly proportional to its absolute temperature at constant volume. So pressure law states that pressure of a given mass of gas is directly proportional to temperature at given volume. That is, volume is constant here. So this means that P by T is constant at a given volume. So suppose at volume V, the temperature of the gas is T1 and the pressure is P1. Let's say that we have increased the pressure to P2, then its temperature will also change in such a way that P1 by T1 is equal to P2 by T2. So this is the pressure law. Now we'll see what is an ideal gas equation. From the three different gas laws that we have just seen, it is clear that pressure, volume and temperature of a given mass of an ideal gas, they are interrelated. So this relation is called ideal gas equation, and the ideal gas equation is written as PV is equal to nRT. Here P is the pressure of the gas, V is the volume of the gas, T is the temperature of the gas, N is the number of moles of gas which is in consideration, and R is the universal gas constant, and the value of R is 8.3145 joule per mole Kelvin. So first we'll see how we arrived at this ideal gas equation. So from different gas laws, that is from Boyle's law, Charles' law and pressure law, we had PV was constant, V by T was constant, and P by T was constant. This was Boyle's law, this was Charles' law, and this was pressure law. So if we combine these three equations, we'll get PV by T is constant. And the ideal gas law says that PV is equal to nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of mole, and R is the universal gas constant. And T is the temperature. The ideal gas equation is always true no matter what is the process a gas is going through. Now we will derive one more equation from the ideal gas equation. This equation states that the density, that is rho, of a gas is equal to Pm by RT, where P is the pressure of the gas, M is the molar mass of the gas, R is the universal gas constant, and T is the temperature. So we have from ideal gas equation PV is equal to nRT. So we can rewrite this equation as P by RT is equal to N by V. Now N is the number of moles of gases. Now N can be written as M by capital M, where M is the mass of the gas and capital M is its molar mass. So we can replace N here with M by M. Now M by V is nothing but mass by volume, that is density, which we represent as rho here. So we have rho by capital M is equal to P by RT, or rho is equal to Pm by RT. So the density of a given gas with the molecular mass M at a given pressure and temperature can be written as Pm by RT. Now we will see what is Avogadro hypothesis. Avogadro hypothesis states that 1 mole of each substance contains same number of particles. This number is called Avogadro number, and it is represented by N, and N is equal to 6.02 into 10 to the power 23 particles per gram mole. Now let's find out what is the number of molecules per unit volume for an ideal gas. This number is equal to P by KT, where K is Boltzmann constant and its value is equal to 1.38 into 10 to the power minus 23 joule by Kelvin. Now we will derive the formula for number density. So from gas equation we have PV is equal to nRT, or we can rewrite this equation as P by RT is equal to N by V. Now in n moles of gas there will be n into Avogadro number of molecules. So if we multiply the both side by Avogadro number, that is n, we will get Pn by RT is equal to n into N by V. Now as we said that n into n is nothing but number of molecules in n moles of gas. So the right hand side becomes our number density, that is number of molecules per unit volume of gas. Now the left hand side we have Pn by RT. Now here we can replace R by N with K, where K is Boltzmann constant. So this is our final equation for number density. As we know that K is R by N, that is 8.3 by 6.02 into 10 to the power minus 23 plus 23, so this will be 1.38 into 10 to the power minus 23 joule per Kelvin. So the formula for number density is P by KT, that is at any given pressure and temperature the number of molecules per unit volume of a gas will be equal to P by KT. Now let's see what is Dalton's law of partial pressure. This law states that the pressure exerted by a mixture of mutually inert gases is the sum of the pressure exerted by the individual gases occupying the same volume alone. So suppose that we have in a container a mixture of 3 gases. Let's say we have a container here and we have gas 1, gas 2 and gas 3. These 3 gases are mutually inert, that is they don't react with each other. So the total pressure exerted by this mixture would be sum of the pressure exerted by the individual gases occupying the same volume alone. Now let's say that the volume of this container is V and the temperature at which this mixture is kept is T. Now let's say that the number of moles of gas 1 is N1, that of gas 2 is N2 and that of gas 3 is N3. So the pressure exerted by gas 1 would be P1. It will be equal to N1, which is number of moles of gas 1 into RT by V, where V is the total volume. Similarly we can write P2 is equal to N2 RT by V and P3 is equal to N3 RT by V, and the total pressure of the mixture of gas will be P is equal to P1 plus P2 plus P3. Now let's see Graham's law of diffusion. This law states that the rate of diffusion of a gas is inversely proportional to square root of the density of the gas. So if the rate of diffusion is R, then R is directly proportional to 1 by root under rho, where rho is the density of the gas. So from here we can write that R into root under rho is constant, or R1 rho 1 is equal to R2 root under rho 2, or R1 by R2 is equal to root under rho 2 by rho 1. So as we have already derived that density of a gas is equal to Pm by RT, where P is the pressure of gas, M is the molecular mass of the gas, R is the universal gas constant, and T is the temperature. So at a given pressure and temperature, that is when pressure and temperature is constant, we can say that density is directly proportional to molar mass, that is M. So we can rewrite this equation as R1 by R2 is equal to root under M2 by M1. Now we will define the degree of freedom of gas molecule. Degree of freedom for a gas molecule is defined as the number of velocity components needed to describe the motion of a molecule completely in three-dimensional space. It can also be defined as the number of possible kinetic energies associated with the molecule due to its translation along three axes, due to its rotation about three axes, and due to its vibration in various modes. So for example, take the case of a monoatomic gas molecule. So let's say this is our three-dimensional axis, this is our y-axis, x-axis, and z-axis. So a monoatomic gas molecule can have motion along any of these three axes, that is, it can have motion along x-axis, along y-axis, and along z-axis. So here we can associate three translational kinetic energy to this monoatomic gas molecule. Now the monoatomic gas molecule has a zero moment of inertia because they are point mass. So there won't be any kinetic energy which is associated with its rotation about any of the axes. So we have three kinetic energies because of translational motion. Also the rotational kinetic energy is almost zero because the moment of inertia of a monoatomic gas molecule is zero because they are point masses. So there will be zero kinetic energy which is rotational in nature. Also there will be zero kinetic energy for the vibration because a single monoatomic molecule cannot vibrate. So in total we have three kinetic energies which can be associated with a monoatomic gas molecule. So the degree of freedom of a monoatomic gas molecule will be 3. We represent degree of freedom as small f. So f will be equal to 3 for a monoatomic gas molecule. Now similarly the value of f is 6 for diatomic gas molecule, and there is also a formula for degree of freedom. Degree of freedom is equal to 2 by gamma minus 1, where gamma is adiabatic constant. We'll learn about adiabatic constant in further chapters. So for now, keep in mind that degree of freedom for a gas molecule can be given as 2 by gamma minus 1, where gamma is adiabatic constant for that gas molecule. Now let's discuss law of equipartition of energy. This law states that the average kinetic energy per degree of freedom for a gas molecule is half kT, where k is the Boltzmann constant. So for a gas with f degrees of freedom, on an average the total kinetic energy associated with the gas molecule is nRT by gamma minus 1, where gamma is the adiabatic constant for the gas. Now we can derive this formula as well. So according to the law of equipartition of energy, the average energy per degree of freedom is half kT. This is average energy per degree of freedom for a single molecule. So for f degree of freedom, the average kinetic energy would be f by 2 kT, and suppose we have n moles of gas, so average kinetic energy for n moles of gas having f degree of freedom this would be f by 2 into kT into n into capital N, where capital N is Avogadro constant and n is the number of moles of gas. So we know that Boltzmann constant is nothing but R by N, where N is the Avogadro constant. So now we can cancel out Avogadro constant. So we have FRT by 2, FRT into N by 2. Now we have already seen that F is nothing but 2 by gamma minus 1. So replacing F with 2 by gamma minus 1, we are left with nRT by 2. So after cancelling out 2, we get nRT by gamma minus 1. So this is the kinetic energy of n moles of gas having f degree of freedom. Now we will derive the pressure formula for ideal gases. Let's see this animation first. So here we have an ideal gas which is confined in a container. This is one of the gas molecule. The velocity of gas molecule is c, and we have broken down this velocity in three components, that is along x direction cx, along y direction cy, and along z direction, that is cz. So the kinetic energy due to the velocity along x direction would be half m cx square, and kinetic energy due to velocity along y direction would be half m cy square, and due to velocity along z direction would be half m cz square. Here m is the mass of one molecule. Now law of equipartition of energy says that the average kinetic energy per degree of freedom is equal, and it is equal to half kT. So these three kinetic energies must be equal. So from here we get cx square is equal to cy square is equal to cz square. Now the velocity of the molecule is c, where c square is equal to cx square plus cy square plus cz square. Now Cx is equal to Cy is equal to Cz, so we can write that C square is equal to Cx square plus Cx square plus Cx square, or 3Cx square. So we have Cx square is equal to C square by 3. Similarly, we'll have Cy square is equal to C square by 3, and Cz square is equal to C square by 3. So we need to keep this result in mind. Now suppose this molecule, it collides with the wall A, B, C, D. Now the momentum of this molecule before collision will be m into Cx, and momentum after collision would be minus m into Cx, because the collision is elastic in nature, so the velocity of the molecule will reverse. So the change in momentum will be two mcx. Now let the length of this container is A. So here we get 2 mcx as delta p. Now the velocity of the gas molecule along x direction is cx. So after the first collision, this molecule will travel the distance of 2a before colliding with the same wall again. So the time taken by the gas molecule to travel the distance 2a would be delta t is equal to 2a by cx. So after this time interval, the gas molecule will again collide with the wall ABCD. So the average force which is being exerted by this gas molecule due to this collision would be F equal to delta P by delta T, which is equal to 2 mcx by 2a by cx. So the average force is mcx square by a, where a is the length of this container, and let's say that b is the width of this container and c is the height of this container. So now we have that the average force exerted by a gas molecule due to the collision with the given wall is mcx square by a. Now let's suppose that the total number of gas molecules inside this container is eta. So the average force experienced by the wall ABCD due to all these molecules would be here eta is the total number of gas molecules and a is the length of container. Now we can replace cx square with c square by 3. So the average pressure which is being exerted by this gas molecule on the wall ABCD would be force by area of this wall, that is b into c, where b is the width of the container and c is the height. So this is our pressure. So we can write now pressure is equal to force, that is nmc square by 3 into bc. Now ABC is nothing but the volume of the container, so we can write pressure is equal to eta into m by 3v. Now suppose that there are n moles of gas inside this container, so number of molecules would be n into n, where capital N is the Avogadro number. So the value of eta, that is total number of molecules, would be n into n if there is n moles of gas inside this container. So we can write P is equal to n into capital N into m by 3v. Now m is the mass of one molecule. We know that the mass of Avogadro number of molecule is nothing but its molecular mass, that is capital M. So the mass of one molecule would be capital M by Avogadro number, that is capital N. So we can again rewrite P is equal to n into n. We can replace m with capital M by n into 3v. Now we can cancel out capital N. So now we are replaced with n into m by 3v. Now the ideal gas equation says that PV is equal to nRT, or 1 by V is equal to P by nRT. So we can replace V with 1 by V with P by nRT. Where P is the pressure. Now Pm by RT is nothing but the density of the gas, that is rho. So now we are left with rho by 3 into c square. Sorry, we left c square here. So finally we get the pressure exerted by gas molecules on a wall as P is equal to rho by 3 c square, where rho is the density of gas and c is its root mean square.